If we see the fluorination of alkanes, basically the direct fluorination of alkanes is not permissible. Why? Question comes, why? Because the reaction with the fluorine is highly exothermic, and because it is highly exothermic, this makes it highly explosive also. That is why direct fluorination of alkanes is never ever permissible. But how do we prepare then fluoroalkanes? We do it indirectly. That is, what we do is we react chloroalkane or bromoalkane with the inorganic fluoride, and it forms fluoroalkanes. Now the reaction of the chloroalkanes or bromoalkanes with the inorganic fluoride to form fluoroalkanes is known as Schwarz reaction. Now let us see an example. Suppose we have RCl and we add inorganic fluoride, suppose Hg2F2, which is known as mercurous fluoride. We also can add antimony trifluoride, that is SbF3. We can also add AgF and so on. If we add suppose mercurous fluoride, then it forms RF, that is fluoroalkane, and it forms Hg2Cl2, which is known as mercurous chloride. Now you can see that in this reaction what is happening is the halogen is getting exchanged. So indirectly we can call this reaction also as halide exchange method. Now as we can see, be it bromination of alkanes or chlorination of alkane or iodination of alkane, or we have fluorination of alkane, basically the reaction keeps on going in the forward direction unless all the hydrogens of the compound are replaced by halogen atom. Suppose we want to stop the reaction at the mono-substituted step, that is in the first step itself. We do not want the alkane to undergo second halogenation reaction, that is mono-halogen alkane is formed. We do not this mono-halogen compound to undergo halogenation again to form a dihalogen derivative. For that matter, what we do is we add alkane in excess and halogen in the trace amount. By this the reaction stops after the first. By this reaction stops after the first step itself. Now let us see the mechanism of free radical substitution reaction, which will tell you about how alkanes on halogenation forms haloalkanes. As I told you that free radical reactions takes place in the presence of sunlight, heat, light, electricity or peroxide. In this example what we have is the sunlight. Basically mechanism of free radical substitution involves three steps. The first step we have is the chain initiation step. Second we have is chain propagation step, and third we have is the chain termination step. In the first step, that is chain initiation, the halogen molecule, that is X2, undergoes homolysis and it forms two X radicals, that is X radical plus X radical. In the next step, that is chain propagation step, X radical formed in the first step will abstract the most reactive hydrogen present in the alkane. The reactivity of the different hydrogens in the compound we will see after the mechanism. Now, if we take suppose simplest alkane, that is CH4, so what will happen is X radical will abstract one of the H of CH4 and forms HX plus CH3 radical. Now, when I was telling you about the reaction, that is halogenation of alkanes, I told you that in each and every step of the halogenation of alkanes, HX is eliminated. In the mechanism now, we can see that how HX is eliminated. Next step we have is the chain termination step. In this step, what happens is the radical, that is CH3 radical formed in chain propagation step will react with X radical formed in the first step. In the first step, that is chain initiation step, we had two radicals. One radical abstracted hydrogen in the second step, so one halogen radical is left. This halogen radical will react with the alkane radical formed in the second step to form CH3X, that is haloalkane. Now, we can see that in the second step, the radical of an alkane is being formed. So, as I told you that radical, that is halogen radical formed in the first step will abstract the most reactive hydrogen. Now, how do we define the reactivity, or how do we compare the reactivity of different hydrogens in alkane? Basically, we can clearly see in the second step of the mechanism we have radical of an alkane. So, suppose X radical in any compound picks up the H from the carbon which is tertiary, so the radical formed in the alkane will be 3 degree. Similarly, if a halogen radical picks up a hydrogen from the compound from the carbon which is attached to 2 carbons, that is 2 degree, then it will form 2 degree radical. And similarly, if a radical, that is halogen radical, picks up a hydrogen atom from a carbon which is attached to a 1 carbon, that means primary carbon, then it will form a 1 degree alkane radical. Now, as we know that 3 degree radical, then we have 2 degree radical, then we have 1 degree radical. This is how we define the reactivity of the different hydrogens in the alkane. Based on this reactivity of the hydrogens, we also can define, or we can also see that what will be the percentage of the haloalkane formed in the reaction. If radical, that is halogen radical, picks up 3 degree hydrogen, then it will form the highest of the percentage in the mixture of the haloalkanes formed in the reaction.